Hello! In this video, we are going to prove the following theorem. The limit as n approaches infinity of 1 plus z over n to the power of n is equal to the sum from k equals 0 to infinity of z to the k over k factorial for all complex numbers z. Now, we have already proven that this infinite series converges for all complex numbers z. And we defined the value it converges to be e to the power of z. Now, before we get into proving this theorem, we are going to prove two lemmas. Here's the first one. For all real numbers x greater than 0, and all positive integers m, we have that the sum from k equals 0 to m of x to the k over k factorial is less than e to the x. So let's prove this lemma. Now, to prove this lemma, let's first give ourselves an arbitrary positive real number x and an arbitrary positive integer m. From here, we want to show that this inequality is true. Well, first of all, what is e to the x? E to the x, by definition, is this infinite series, where z is replaced with x. And this just means the limit of the sequence of partial sums. Right? Now, the claim is that this sequence is a strictly increasing sequence. So how do we show that? Well, all we got to do is show for all positive integers n, the n plus 1th term of this sequence is strictly greater than the nth term of this sequence. So let's give ourselves an arbitrary positive integer n. And from here, we're going to show that the n plus 1th term is strictly greater than the nth term. Well, let's write out the n plus 1th term. And now, let's pull away the n plus 1th term of this sum. So we get this. But remember, since x is greater than 0, we know x multiplied by itself n plus 1 times will also be greater than 0. Divide that by n plus 1 factorial, still greater than 0. So this guy must be greater than 0. Therefore, this guy must be greater than this guy. So we have shown, given any positive integer n, we have that the n plus 1th term of the sequence is strictly greater than the nth term of the sequence. And therefore, this sequence is strictly increasing. So this sequence is an increasing sequence, but it's also convergent. If you recall, by the monotone convergence theorem, it follows that the value that this sequence converges to is the least upper bound of the terms of this sequence. So e to the x is the least upper bound of the terms of the sequence. So now, since this sequence is strictly increasing, we know that the nth term of the sequence is strictly less than the n plus 1th term of the sequence. But remember, e to the x is the least upper bound of the terms of the sequence. And therefore, e to the x is an upper bound of the terms of the sequence, and by definition of an upper bound, this means every term of the sequence is less than or equal to e to the x. So in particular, the n plus 1th term is less than or equal to e to the x. And hence, the nth term is strictly less than e to the x. So we have proven exactly what we wanted to prove. So this completes the proof of lemma 1. Now let's look at lemma 2. Suppose a0, a1, am is a list of real numbers, all between 0 and 1. Then the product 1 minus a0 times 1 minus a1, times 1 minus am is greater than or equal to 1 minus the sum a0 plus a1 plus plus am. So, to prove this lemma, we're going to use induction on n. So, the base case will be m equals 0. Now, in the case m equals 0, we're going to give ourselves a real number, a0, between 0 and 1. From here, we want to show that this inequality is true. Well, if we start out by writing left-hand side, we have this, but remember, when the lower and upper number of a product are the same, we know that we just replace I with a 0. So we get this, but then a0 is the same thing as the sum from I equals 0 to 0 of ai. Right? So this guy is equal to this guy. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer m greater than or equal to 0. And we assume for any list of numbers from a0 to an, all between 0 and 1, we have that this inequality is true. So now, we want to show that this is also true for n plus 1. So, to prove it's true for n plus 1, let's give ourselves an arbitrary list, a0, a1, an plus 1, all between 0 and 1. And from here, we want to show that this inequality is true, where instead of m, we have n plus 1. Well, let's start out by writing the left-hand side with n plus 1. Now to start, if we pull away the n plus 1th term of this product, we have this, but then we know by the induction hypothesis that this inequality is true. So let me just write this inequality down here. Now, since am plus 1 lies between 0 and 1, it follows that 1 minus am plus 1 also lies between 0 and 1. So 1 minus am plus 1 is greater than or equal to 0. So if we multiply it on both sides of this inequality, the sign of the inequality will remain the same. So this is what we get. And this shows that this guy is greater than or equal to this guy. Now, if we expand this out, what are we going to get? We have 1 minus the sum minus am plus 1 plus am plus 1 times the sum. Now, the claim is that this guy is greater than or equal to this. Because notice, we know am plus 1 is greater than or equal to 0. Further, every term in this sum is also greater than or equal to 0. Therefore, the entire sum must be greater than or equal to 0. So we're multiplying two numbers which are both greater than or equal to 0. So therefore, this entire thing must be greater than or equal to 0. And because this thing is greater than or equal to 0, that tells us that this guy must be greater than or equal to this. And then let's factor out a minus sign. And this is what we get. But then we know if we add these two together, this is just the sum from I equals 0 to n plus 1 of ai. And so what we have shown here is that this guy is greater than or equal to this guy. So basically we've shown that this is true, where instead of m, we have n plus 1. So this completes the induction step. And so this completes the proof of lemma 2. So now we've proven both lemma 1 and lemma 2. So we're going to prove the main theorem. So we want to prove that these two values are equal for all complex numbers z. And we're going to split this up into two cases. The first case is z is equal to 0. The second case is z is not equal to 0. So let's first suppose that z is equal to 0. Now in this case, we want to show that these two values are equal. Now, to show that these two values are equal, what we can show is the following. We can show that these two sequences are constant sequences of ones. If we can show that, then these two sequences both converge to 1, and therefore these two values are equal. Right? They're both equal to 1 in this case. So to show that these two sequences are constant sequences of ones, what we're trying to show here is, for all positive integers n, the nth term of this sequence is a 1, and the nth term of this sequence is a 1. So let's give ourselves an arbitrary positive integer n. Well then, let's write out the nth term of this sequence. Well, we see that 0 divided by n is 0, 1 plus 0 is 1, 1 to the power of n is 1. So the nth term of the sequence is a 1. Now let's show that the nth term of this sequence is a 1. Well, if we write out the nth term, we have this, but now let's pull away the k equals 0 term of this sum. If we do that, we get this. Now it looks a little strange because we have 0 to the power of 0. But the definition of exponentiation that we are working with here is the following. We're working with this definition, right? So in particular, if we take z to be 0, we define 0 to the power of 0 to be 1. This definition is often used when we're working with power series. So yeah. So in this case, 0 to the power of 0 is 1, divided by 0 factorial, that's still 1, so we have 1 plus this sum. But now, if we consider an arbitrary term of this sum, well then k is a positive integer. So 0 to the power of k is 0, divided by k factorial, it's still 0. So really, we just have the sum of a bunch of zeros, which is just 0. So we have 1 plus 0, which is just 1. So we have shown that the nth term is equal to 1. So since n was arbitrary, we have shown that both of these sequences are constant sequences of ones. And because they are both constant sequences of ones, they must both converge to 1, and therefore these two limits are both equal to 1. So this covers the case where z is equal to 0. So now we are going to consider the case z is not equal to 0. Now, it suffices to show the following. It suffices to show that the limit of this sequence is equal to 0. So essentially, the limit of the difference between these two sequences. So why is this sufficient? Well, what happens if we have shown that this is true? Well, remember, we know that this infinite series converges, and the value we defined it to be is e to the power of z. Put another way, this infinite series is the same thing as the limit of the sequence of partial sums. So if we know that the limit of this sequence is equal to e to the z, and the limit of this sequence is equal to 0, well then from properties of limits, it follows that the limit of the difference between this sequence minus this sequence is equal to e to the z minus 0. And that's just equal to e to the z, and e to the z is just equal to this infinite series. But what is this difference? This difference is just 1 plus z over n to the power of n. Right? These two sequences are the same, so they must converge to the same value. Now, it doesn't matter the starting index, so that's why we typically write this rather than specifying the starting index. So we'll just get rid of this. And so we will have that the limit of this sequence is equal to this infinite series, which is exactly what we want. That's why it suffices to show that the limit of this sequence is equal to 0. Now, how do we show that the limit of this sequence is equal to 0? Well, we're going to use the definition of the limit of a sequence. So to show that this sequence converges to 0, we're trying to show for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of the nth term of this sequence is less than epsilon. So to prove that, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer capital N, such that for all n greater than or equal to capital N, the absolute value of the nth term of the sequence is less than epsilon. Now, I could tell you what capital N is right now, but instead of telling you what it is directly, we are going to figure out what to choose capital N to be as we go through the proof. So for now, I'm just going to write star, 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 and we're going to figure out later in the proof what we should write here, right? So we're pretending as though we've already figured out what to choose capital N to be. With this choice of capital N, let's give ourselves an arbitrary integer n greater than or equal to capital N. And now, let's show that the absolute value of the nth term of this sequence is less than epsilon. Before we actually get into that, let's re-express this guy in a different way. Now, the binomial theorem works for complex numbers. So applying the binomial theorem, we know that this guy is equal to this. Now, we know that n choose k is just n factorial over k factorial times n minus k factorial. We know that z over n to the k is just z to the k over n to the k. And then 1 to the n minus k is just 1, so this is what we have. Now, I'm just going to swap k factorial and n to the k. So we have this. So now, we are going to re-express n factorial in terms of n minus k factorial. And what that would look like is something like this. So we have n factorial, which is equal to n times n minus 1 times n minus 2, and so on and so forth, up until n minus k minus 1. And then after that, we have n minus k factorial, right? So these two guys are equal. Now in product notation, it's just this. So as you can imagine, this product goes from I equals 0 to k minus 1. So we have n times n minus 1 times n minus 2 all the way up to n minus k minus 1 times n minus k factorial. It's precisely the same as what we have above. So this is just re-expressing n factorial in terms of n minus k factorial, but also we can re-express n to the power of k as the following. It's just the product from I equals 0 to k minus 1 of n, right? We're just multiplying n by itself k times, right? Because as you can imagine, how many integers are between 0 and k minus 1? K. So these two are equal. So we're just going to re-express n factorial as this, and n to the power of k as this. So we get this, and we see that the n minus k factorials are going to cancel out. Also, we can combine these two products into a single product, right? Really, we have a ratio of products. Well, a ratio of products is the same thing as the product of the ratios. So we get this, right? We just combined n minus I over n into a single product like this. So now we can rewrite n minus I over n as n over n minus I over n. Well, that's just 1 minus I over n. And so this is where we end up at. So this is as far as I wanted to go in terms of re-expressing this guy in a different way. So let me just go back up to the top and write down that this guy is equal to this guy. Now, since we've ran out of room, let's move back up to the top. So now, remember, we want to show that the absolute value of the nth term of the sequence is less than epsilon. That is the whole goal. And to show this, well, let's first re-express 1 plus z over n to the power of n as this. Now, we can combine these two sums into a single sum. Really, the sum of these guys minus the sum of these guys is equal to the sum of these guys minus these guys. And now we're going to factor out z to the k over k factorial. We'll factor out on the right-hand side. So then next, let's apply the triangle inequality. Right, we know that the triangle inequality tells us the absolute value of a sum is less than or equal to the sum of absolute values. So we get this. And now we know that the absolute value of a product is equal to the product of absolute values. So we're going to split this absolute value up into the absolute value of this guy times the absolute value of this guy. Well, if we do that, we get this. And first of all, let's deal with absolute value of z to the k over k factorial. We know that the absolute value of a fraction is equal to the absolute value of the numerator over the absolute value of the denominator. So we get this, but we know that the absolute value of k factorial is just k factorial. And a property of absolute values tells us we can pull the k to the outside of the absolute value. So really, we can re-express this guy as this. Now the claim is we can remove these absolute values. And to show that, well, if we consider an arbitrary term of this sum, that is, we consider an arbitrary integer k between 0 and n, well, first of all, if k is equal to 0, then here we have the product from I equals 0 to -1. Well, since the lower number is bigger than the upper number, this is just an empty product. And we know by definition, an empty product is just equal to 1. So we have 1 minus 1, which is 0, and so we can get rid of the absolute values. That covers the case k is equal to 0, otherwise k is strictly greater than 0. If k is greater than 0, then we're actually going to have terms in this product. Now, if we consider an arbitrary term in this product, that is, we consider an arbitrary integer I between 0 and k minus 1, well then, k minus 1 is less than k, and k is less than or equal to n. So 0 is less than or equal to I, which is less than n. Therefore, if we divide n over, we have I over n lies between 0 and 1. From here, it follows that 1 minus I over n also lies between 0 and 1. And therefore, we see that every term of this product lies between 0 and 1. Well, a product of a bunch of numbers between 0 and 1 will also be between 0 and 1. So we have 1 minus a number between 0 and 1, which is greater than or equal to 0. So this quantity is greater than or equal to 0, so we don't need the absolute values. So what this tells us is no matter what k is, we can always remove these absolute values. So now we are going to apply lemma 2. To apply lemma 2, well, first of all, if we consider an arbitrary term of this sequence, or in other words, consider an arbitrary integer k between 0 and n, well, if k is equal to 0, we can all agree that this inequality is true. Because if k is equal to 0, then we have a product from I equals 0 to negative 1. So this is an empty product, and by definition, an empty product is just equal to 1. This is a sum from I equals 0 to negative 1, so it's an empty sum. And by definition, an empty sum is equal to 0. So we have 1 on the left-hand side, 1 minus 0 on the right-hand side, so both these guys are equal. So this is true in the case where k is equal to 0. Well, we could also show, if k is greater than 0, that this is true. Because if k is greater than 0, well, let's go to lemma 2. We're going to take m to be k minus 1. And so we're going to take a0 to be 0 over n, a1 to be 1 over n, and so on and so forth. Ak minus 1 will be k minus 1 over n. In general, we're taking ai to be I over n. Well, we can show that all of these guys lie between 0 and 1. Well, actually, we already showed that. Because, if you recall from earlier, we showed I over n lies between 0 and 1, where I was any integer between 0 and k minus 1. So yeah, all of these guys lie between 0 and 1. Therefore, we can conclude that this is true, where m is equal to k minus 1, ai is equal to I over n. But that's precisely what this is. So this is true if k is equal to 0 and if k is greater than 0. So no matter what k is, this is true. So what can we do with this? Well, notice in our sum, we have 1 minus this product. So if we subtract this over to the other side and add this over to the other side, we get this. But then we know that since n doesn't depend on the index I, we can pull the n to the outside of the sum. So we get this. But we know what this sum is, right? This is just 0 plus 1 plus 2 and so on and so forth up to k minus 1. In general, we have the following. For all integers m greater than or equal to 0, the sum from I equals 0 to m of I is equal to m times m plus 1 over 2. Right? We have m greater than or equal to 0 here because we actually have terms in this sum. But it turns out this will also be true if m is equal to negative 1. Because what happens if m is equal to negative 1? Well, then we have the sum from I equals 0 to negative 1. Well, that's just an empty product. So the left-hand side, an empty sum. So the left-hand side would just be 0. But on the right-hand side, we get negative 1 times negative 1 plus 1 over 2, which is also equal to 0. So if m is equal to negative 1, this is also true. So in particular, since k is greater than or equal to 0, k minus 1 is greater than or equal to negative 1. So if we take m to be k minus 1, What do we get? Well, I'm going to replace m with k minus 1. We have this. So really, this just simplifies down to k times k minus 1 over 2. And so we have that this guy is less than or equal to this guy. And I've ran out of room, but if we take this inequality and multiply absolute value of z to the k over k factorial on both sides, we get so all we've done here was we multiplied both sides of this inequality by absolute value of z to the k over k factorial. We get this. So what does this tell us? It tells us that every term of this sum is less than or equal to this corresponding value. Therefore, the sum of all of these guys must be less than or equal to the sum of all of these guys. So this part is essentially the turning point of the proof, right? Things are going to start coming together. Now notice, we would like to re-express k factorial as k times k minus 1 times k minus 2 factorial, because then we'll be able to get rid of the k times k minus 1 right here. But we can't re-express k factorial as k minus 2 factorial if k is equal to 0 or k is equal to 1, right? So what we're first going to do is we're going to pull out the k equals 0 term and the k equals 1 term from this sum. But we can't do that either if n is too small. But that's okay, because remember, n is greater than or equal to capital N. And we get to control how big capital N is. So if capital N was, say, bigger than 100, then n would be bigger than 100. So we have more than 100 terms in this sum. So certainly we can pull away the k equals 0 and k equals 1 term from this sum. So if we do that, here's what we get. We get this, right? This was the k equals 0 term, this was the k equals 1 term. But notice, both of these guys are equal to 0, so we're just left with this. Now at this point, let's just move back up to the top. So now, since k is at least 2, we can re-express k factorial as k times k minus 1 times k minus 2 factorial. And let's also re-express absolute value of z to the k as absolute value of z to the k minus 2 times absolute value of z squared. So notice k times k minus 1 will cancel out with k times k minus 1. But then, since absolute value of z squared over 2n doesn't depend on the index k, we can pull them to the outside of the sum. And now, let's decrease both the lower and upper number by 2, so we get the sum from k equals 0 to n minus 2. Right, we can do that. All we have to remember is we have to increase everywhere we see a k to k plus 2. So if we do that, we get this. So these two sums are the same. But now we apply lemma 1. If we take x to be absolute value of z, and we take n to be n minus 2, then this guy is less than e to the power of absolute value of z. And since this guy is less than e to the power of absolute value of z, it follows that this guy is less than this guy times e to the power of absolute value of z. So we get this. But then we see, if we were to let n approach infinity, this quantity would essentially become 0. So now, we're ready to define what capital N should be. you recall from earlier, we had star, star, star. Well, here's what we're going to put here. We can choose a positive integer, capital N, such that capital N is greater than the following value. We choose a positive integer, capital N, such that capital N is greater than 100, and capital N is greater than absolute value of z squared times e to the power of absolute value of z over 2 epsilon. Now, this is sort of a crude estimate, right? You could definitely choose capital N so that capital N is greater than a smaller value than this. The point of this is just so that we could pull away the k equals 0 and k equals 1 terms of this sum from before, right? But now, this is useful because since we know n is greater than or equal to capital N, this tells us that n must be bigger than this. So, dividing n over and multiplying epsilon over, we get that this guy is less than epsilon. And so, we started at the absolute value of the nth term of that sequence, and we showed that it's less than epsilon. Therefore, we had that the limit of the sequence is equal to 0. And that was enough to tell us that these two values are equal. And so this completes the proof. And so yeah, that's pretty much it for this video.